Hello everyone, welcome to topic 714, free energy of dissolution. By the end of this, you should be able to explain the relationship between the solubility of a salt and changes in enthalpy and entropy that occur with the dissolution process. Please note that we will come back to this and look at it in more detail in a future unit. I believe it is unit 9. Okay. So there are two driving forces that determine the spontaneity of a reaction. Spontaneity is another way of describing if a reaction will take place. It does not mean that the reaction will take place quickly. It just states that the reaction will happen without any external forces. So if you think of the decomposition of hydrogen peroxide into water and oxygen, that is a spontaneous reaction. It does happen naturally, without any outside forces. But it does not happen very fast unless you add outside forces like a catalyst or expose it to light. The first driving force for reaction spontaneity is enthalpy. Exothermic reactions are favored. Some dissolution reactions are enthalpically favorable, but others are not. The second driving force is entropy. Entropy is often described as a measure of the disorder of or randomness of the energy in a system. But another way to describe it is to think of the probability of the particles or energy being distributed into microstates. Essentially, all the tiny particles within a container. So, we'll just keep going and then maybe, yeah. Entropy is given the designation S, with positive values meaning that the system is increasing in entropy, and negative values mean that the system is decreasing in entropy. The universe moves towards greater disorder, so positive entropy is favored. So, this is kind of like your bedrooms, where, you might try and keep it organized, but it always does end up getting messy, or, let's be real, Miss Bert's room, I try on occasion to tidy up and get things organized, right? But the universe does not favor that. My room tends towards disorder, and then I have to try and bring it back in check. But disorder and a little bit of craziness is favored. Okay. So consider a solution at 298 Kelvin. The particles are moving within the container and have kinetic energy. If that same solution were heated, the particles would be moving more rapidly with greater kinetic energy and would therefore have greater entropy. This is because the faster they move, they can be in a more, or potentially more, random combinations of, organization or disorder. They have multiple spots where they could be if they're moving faster compared to when they're moving slower. Likewise, mixing two substances or dissolving a solid will generally increase the entropy of the system because volume increase leads to more available microstates or positions that the particles can occupy. Thus, the probability of these particles and their energies occupying the different microstates increases. This means that solution formation is usually entropically favorable. Now, there's always exceptions to every rule. The two driving forces, entropy and enthalpy, are linked together through Gibbs free energy, which we will come back to in Unit 9. If the enthalpy and entropy are both favorable, the reaction will proceed all the time. If the enthalpy is unfavorable, then the reaction will proceed only at high temperatures. If entropy is unfavorable, then the reaction will only proceed at low favor. So what this is saying is for it to always be favorable, our delta H has to be negative and our delta S has to be positive. Right? In this case, we're looking at when the entropy is positive and the entropy and enthalpy are both positive. So this is only favorable when the T is so big that the entropy overwhelms in this equation. Then if we look at the delta, if we look at what happens if we have negative enthalpy and the negative entropy. It's only possible at low temperatures. So our enthalpy is so favorable that, and then it's a low temperature, that the entropy factor doesn't overwhelm it. If the enthalpy and entropy are both unfavorable, so that means that enthalpy is positive and entropy is negative, the reaction will not proceed under any circumstance. There are three processes that occur when a solution is formed, and how these combine give us the overall favorability of the solution. So when the intermolecular forces between solvent particles are overcome and solute particles are overcome, notice this creates more disorder, so that's favorable. But the bond breaking process, even if it's intermolecular forces, requires energy. So enthalpy is positive and thus it's unfavorable. But then when the interactions are again reformed between our intermolecular forces, and we get this negative because that's a release of energy, that is favorable, but now we're reducing the number of microstates that these particles can occupy because they're now having to interact and be in specific spots. There is some organization required because of solute and solvent intermolecular force interactions that makes this one unfavorable. How these all combine together gives us whether or not the Gibbs free energy is positive or negative, and thus the process favorable or unfavorable. Okay, so let's look at some example problems. Which solution would have greater entropy with all other factors remaining equal? Justify your answer. So looking at this, we see that the number of ions that are formed in both, if we look at it, it's going to be the cation for both and then 2 hydroxide ions. So it's a total of 3 ions that are released in the dissolution process. So it's not going to be that one creates more disorder because it has more particles, okay, because they have the same number of particles. So now we're going to look at their solubility products. Well, we see that A is technically more soluble, right? It has a higher KSP value, right? Negative 15 is bigger than negative 22. So since the KSP for our cobalt hydroxide solution is bigger, A will have greater entropy. Because it is more soluble. Okay, so now if we look at the dissolution of calcium chloride is exothermic. Draw a model of the following. So if we draw water, right, and draw a couple water molecules, where this is my oxygen, that's O, and this is hydrogen. Okay, and then if we draw calcium, we could draw calcium as an X and chlorine chlorine's going to be red. Okay, so there's chlorine and calcium, so this is calcium and this is chlorine. So when we draw calcium and chlorine, we have 1 calcium for every 2 chlorides, and so we're going to draw that repeating pattern. And we don't have to draw a bunch. Okay, then when it's aqueous, we should show that the chlorine in ratio, so there's 2 chlorines and 1 chloride, and that the water molecules are going to orient around those and create a hydration shell. So the negative end of the water molecule is going to point towards, and they shouldn't touch, my bad, point towards the calcium, and then the positive end of the water molecule is going to point towards the chloride.
Morning, Miss Burt.
Good morning, Mr. Delbridge. You are now permanently immortalized in one of my AP videos.
Oh no, why?
Because I'm recording lecture notes.
Cause what?
I'm recording lecture notes.
Oh, I'm sorry.
No, you're good. So, good morning, Mr. Delbridge, and thank you all for tuning in.